taking the time to review some of our acid-base chemistry, including now looking at anilines. Okay, aniline has a pK of 4.6. A regular amine has a pKa of about 10. Did we say this last time? Okay, it's a pKa. You got to know what that means. That refers to the conjugate acid. Basically, pKa of 10 means this is more basic. Why is it more basic? This lone pair is in an sp3 orbital. It's localized. It's not delocalized by resonance. This lone pair is in what type of orbital? P orbital. Now, in organic 1, I said also here, if the lone pair is in a p orbital, it's not basic. Typically, it is not basic. This is one exception. Yes, it's delocalized, but because it's delocalized on the carbon, it's not delocalized a lot. So it's slightly basic still. It's not as basic as this. Okay? pK refers to that. Now, in terms of substituted anilines, let's see, once we put a substituent group here, what if it's electron withdrawing group net? What is that going to do? Well, let's forget about what it says. Let's rationalize what it will do to this lone pair. We know it's conjugated. Is this electron withdrawing group going to pull that lone pair towards it?
Yes.
What does electron withdrawing mean? Yes. If we pull this lone pair more into the ring, what is that going to do to the availability of that lone pair to go out and grab with a proton? It will reduce the likelihood of it doing that. So it's less basic with electron withdrawing group. Okay, that means lower pKa. You've got that straight. Now, what if we put a donating group and we push electrons towards the lone pair? What's that going to do to the electron density at the lone pair? We're pushing electrons towards it. It's going to increase the electron density there. So if we increase the electron density, it's going to be more electrons there in terms of density. That will make it more basic. You need to rationalize this, not just memorize them. Now this is opposite than the acids, because with an acids, electron withdrawing group would stabilize the resulting minus, making it more acidic. If you rationalize it, it can be very straightforward. It's only when you start trying to memorize something does it become jumbled up in your head. For over here, compared to aniline, pK of 4.6. Put a nitro here. Is this going to be higher pKa or lower? Lower pKa. I'm talking about with the group compared to aniline. How about this guy?
Higher.
Yeah, higher pKa, because this is a net what? Net donating group. As long as it's pair or ortho. Let's look back on the previous page. Anybody rationalize why this, with the methoxy's para, it's less acidic, but when it's meta, it's more acidic? Anybody rationalize that or have an answer to why? Matt?
Is it because it can't donate with resonance when it's meta?
It can donate to the ring. What do you mean it can't donate?
Well, you can't draw an extra resonance structure if it's meta.
Right, if this was an OME, we can draw a resonance structure. I'll do it all at once here. Electrons in. I really don't have my pi bonds drawn there sufficiently. We do it all at once, electrons here, electrons here, electrons there, electrons up. And we can get resonance structure basically, this lone pair is conjugated all the way through here, and we can shove donation of the lone pair into the carbonyl. You can do this stepwise and arrive at this. Over here, we cannot. You can never draw a resonance structure where these electrons are delocalized into that carbonyl. You should try and see that you cannot do that. These electrons pump more electron density into that carbonyl than this. So why is it more acidic than if there was nothing there? The fact that it's more acidic tells you that this is acting as what type of net group? It's a net withdrawing group. That's what that number tells you. Why is it a net withdrawing group? Didn't we learn that an O is a donator? Yes, and here it's donating. But here it cannot donate to the group. But in addition to donating by resonance, what does an oxygen also do? Withdraws by induction. So we take from this number, which can be determined in the lab, we take that the major effect here is what? Apparently the major effect is withdrawing by induction. We rationalize that by saying, yeah, it's doing that. Since it can't be localized into the carbonyl, the resonance is not as great, where this one can. Okay? I'm not giving you full details here. It would take 30 minutes to draw it all out. You need to sit down and rationalize it to yourself. So in the end, you just can't blindly look at these groups. Okay, now at the very bottom, aniline can also act as an acid. I mean, it's not an acid, but anything can act as an acid. That is, it can give up an H and become that minus. If you're looking at that reaction, or this equilibrium, that equilibrium has a pK of about 30, 28 to 30. Okay? Because this refers to this being an acid, where the pKa of 5 refers to the positive being an acid. Which is more acidic, this or the protonated version? Protonated version, clearly more acidic. It's more eager to give up a plus and go neutral. Much more acidic, pK of 5. Less acidic. It doesn't want to become minus as much. Less acidic. Okay, one last thing we look at with acid base is to remember the extraction process. We're separating acidic, basic, neutral molecules. If you look at the 4 up there, the first compound is acidic. That's a carboxylic acid. The second compound is acidic. It's a phenol. Now, it's not as acidic as the first compound. The third compound is what? Basic. Now, it can act as an acid, but the first is to be basic. And under aqueous conditions, it can only be basic. And the fourth compound is what? Acid, base, or what? Fourth compound is neutral. It's not going to act as an acid or a base, especially under acidic conditions. How could you separate these? You had a mixture of all 4 in a flask. You could dissolve all 4 in an extraction solvent. Here they use tert-butyl methyl ether, or MTBE. I don't know why they would use that. That's an odd extraction solvent. I would use dichloromethane or ether, or maybe ethyl acetate. If we mix with bicarbonate, shake it up, you get 2 layers. Which one will go into the bicarbonate layer? Well, here's your first answer. Bicarbonate layer is aqueous. Which one will go into the aqueous layer? The one that becomes ionic in the presence of bicarb. Which one will become ionic in the presence of bicarb? Somebody said 1, 2, and 3. Not 3. 3 is a base. Bicarb is a base. Only compound 1 will. We said earlier, carboxylic acids are acidic enough to react with bicarb, but phenols are not. Compound 1 becomes an ion pair. It goes into the water layer. The other 3 stay in the organic layer. You separate your layers. You have this separated. How do you get back this to the neutral form? You add an acid, put the H back on. Now you got these 3 in the organic layer. Now you can add in hydroxide, a stronger base. Of 2, 3, and 4, which one will become an ion in the presence of hydroxide? Compound 2, phenol. So it becomes an ion pair. It goes into the aqueous hydroxide, separating from these 2. You separate it. If you want to put the proton back on, you add a strong acid. Now how do you separate these 2, 3 and 4? What type of properties does any of them have? Can you convert one of them to an ion pair? Compound 3 can be converted to an ion pair by treatment with what? An acid. So you now add in like HCl. Compound 3 becomes protonated, becomes an ion pair. It goes into the aqueous layer. You're not going to protonate that guy. It stays in the organic layer. You separate your layers. How do you get the neutral compound? Here you have to take a proton off. How do you take protons off? Aqueous base. Now you have them all separated, and at the very end, you rotovap off your extraction solvent, and you have this in your flask. Very often, this is soluble in aqueous base. When you add acid, it's no longer soluble, and this will precipitate as a solid. You just filter it off. Phenol won't precipitate. You have to extract it, and these 2 won't, but if you're lucky, your product is a solid and it just precipitates when you make it neutral. Okay, so in the end, please review your extraction processes. Basically, that also requires you to review your acid-base chemistry. All of this is equilibria. I mean, what's the pK of this? pKa describes an equilibrium. What is this an equilibrium with? That up there. What's the pKa of this? 5. What's the pK of HCl? -8, something like negative. Okay. Really, that's not 5. The acid on that side is -8. What's the acid down here? 5. Which is favored, -8 or 5? 5. By how much? 10 to the 13th. That's a lot. You add HCl, you're going to put the proton on. Okay? That's the same old thing ever since week 3 of Organic 1, using your pKa's to determine your equilibrium. Okay. Trying to move through this because it should be mainly review, or you need to sit down and do it on your own. I can't spend 45 minutes explaining something right here. Let's see what else is here. Well, I haven't quite got there yet. Eventually we'll get to scratch and sniff. Y'all know scratch and sniff? Okay, lots of esters. When we cover esters, you can look back at that. Okay. So now we're ready to start the chemistry of acid derivatives. Now we can maybe start with this sheet here. This is the sheet I put together. And acid derivatives, one of the main things we'll be looking at is converting one to another. How do you convert a carboxylic acid to an ester? This shows sort of what's called the interconversion of your acid derivatives. We start at the top. Carboxylic acid is the king. They can be converted to a variety of derivatives. Acid chlorides, also known as acyl chlorides. We just use these for Friedel-Crafts acylation. Can be converted to an ester. We haven't said what this functional group is, but that's an anhydride. Some of you used an acetic anhydride in lab. Acid chlorides can be converted to anhydrides, esters, or what's that down there, amides. All of this is interconversion. Eventually what I want you to do here is on every arrow put reagents. What reagents would be needed here to convert this to this? What reagents? Okay? So as you go along, you work to fill this in, and this is some organization. Now, what we will learn is everything in the box, those are all acid derivatives. First off, they're listed in terms of reactivity. Higher up. Acid chlorides are more reactive than amides. But more reactive towards what? Towards a nucleophilic addition. Everything in the box can be hydrolyzed with aqueous acid back to what? Carboxylic acids. So they can all revert back to the king, carboxylic acid. You can also get back to not using aqueous acid, but what does it say down here? Aqueous base. Now when you do aqueous base, your carboxylic acid is going to be in the basic form. If you knit a sweater in the pool, it's going to be wet, right? Basic form, basic condition. How do you put the proton on? Well, you got to throw in some acid to put the proton on. When you throw in the proton, you get back to your neutral carboxylic acid up top. Okay? All right. Now the green is our outline. And it's pretty thick. Number of mechanisms we're going to look at for this chemistry. Aromatics, we looked at 3 mechanisms. Here we're going to look at mainly just one mechanism. All this stuff is mainly just one mechanism. And if you learn that one mechanism and all the subtleties and the slight variations that go with it, you really know a lot here. There's just a lot of examples. Okay. First thing we're going to do is look at synthesis of carboxylic acids. And the first thing is going to be a review of previous methods. Okay? So please be going along the green sheet. I would not always go over there and look at it, but that's what we're going to be doing. So, first thing is synthesis of carboxylic acids. A review. How have we synthesized carboxylic acids before? First way, benzylic oxidation. React this with KMnO4, what do you get? Carboxylic acid. What other ways have we made carboxylic acids? What about oxidation of primary alcohols? Make primary alcohol, one of the big 3, what do you get? Carboxylic acid. What's the intermediate? You first get the aldehyde, and then it's further oxidized with one of these to the carboxylic acid. Or if you just have an aldehyde, what special reagent did we use for just oxidation of aldehyde? Toluenes. Of course, the big 3 would do this also. How about another way that we've made carboxylic acids? What about cleavage of alkenes? If you take this with KMnO4, you can cleave the alkene with heat. Each carbon becomes carbonyl. But if one of them is an aldehyde, what happens to the aldehyde in the presence of KMnO4? Becomes carboxylic acid. And so there's other examples down here. And if we compare that to ozonolysis, If this is cleaved with KMNO4 heat, you get ketone acid. Ozonolysis with zinc or dimethyl sulfide workup, you get ketone aldehyde. Aldehyde survives ozonolysis if you work it up with zinc or dimethyl sulfide. Everybody remember all those syntheses? Those are all carboxylic acids. Okay. New ways. I reckon it's on the green. Now let's look at some new ways. There's going to be two new ways. The first is going to involve a Grignard. We know that. Treat this with magnesium, you can get this Grignard. This is essentially that carbanion, right? Well, a very neat reaction. If you throw in CO2 gas or even dry ice, CO2, throw in some dry ice, carbon dioxide looks like this. This carbon is pretty electron poor because we have two oxygens pulling. So there's a good amount of partial plus there. This minus will be attracted there, and these electrons add to the carbon. Well, something has to leave. This carbon can't have 5 bonds. These electrons get pushed over onto one of the oxygens. That oxygen's happy now because it gets more electrons. What does this give? Well, it gives that right there. I'm not going to redraw it. What bond did we just make? We just made that terminal carbon bonded to that carbon there, pushed electrons over here. What does this arrow mean? You now have 3 lone pairs there, and you get that. That's just a Grignard adding to CO2. Very versatile reaction. That's just a carboxylate in the basic form. If you add in H plus workup, you can put the proton on, and there you go. You just made a carboxylic acid by making that bond, with this being your Grignard that came in and added CO2. Hopefully that looks pretty straightforward. Yeah? Just need to sit down and do the mechanism a couple of times. By the way, there's a handful who still just do not know how to appropriately use arrows or mechanisms. Okay. Ultimately, what did we start here? We started with an alkyl bromide halide. Okay. Down here, we also started with the same alkyl halide. Down here, we're going to use cyanide as a synthon, carboxyl synthon. Synthon is sort of, it's like a precursor. It's a surrogate or a precursor. If we first do a sodium cyanide, we can do, what's that, SN2? And we can get a cyano on there. Now your cyano is actually an acid derivative, if you remember. 3 bonds to a more electronegative atom. And back over here on the right, what did we say that could happen to all acid derivatives? Here's your nitron. All acid derivatives with aqueous acid are converted to what? Carboxylic acid. And so, aqueous acid and heat, it does require some heat. We'll do this mechanism a little bit later when we look at nitrile chemistry in particular. We get the carboxylic acid. The nitrogen comes off as ammonia, NH3, but how will NH3 exist under acidic conditions? NH4+, because ammonia is a base. Now, you can also do this with aqueous base. If you do that, it requires an H+ workup, just like was on the other sheet. Again, we'll look at this mechanism, both of these later. So ultimately, it's two different ways to go from here to the acid. Note, in both cases, this is 3 carbons, but this is how many? 4. Where did the other carbon come from? CO2. Where did the other carbon come from here? See, this is 3 C's. That's 1, 2, 3, 4. The other carbon comes from the cyanide. Okay. The cyanide approach does have a limitation. Show the Grignard approach and the cyanide approach to making this. Just kind of sketch it out. And then look at them and tell me which one is not really going to work in this case. Basically show a synthesis of that using one of the reactions we just introduced. Let me walk you through it. Let's see, I'll back it up to, I know this could come from a cyanide. So we come from that. If I have that, how do I get this? H3O plus heat, right? How do you make this? We back it up to be something like this, plus what? Sodium or KCN in the sunshine band? Okay. Anybody see any problem with this? This is tertiary. And you don't do SN2 on tertiary halide. This ain't going to work. You don't do SN2 on tertiary halide. But we can back this up to Grignard plus what? Plus CO2. And we can get that with H+ workup. How do you make this? You treat this with magnesium. See, that works. You can make a Grignard of that. But you can't do SN2. So in that particular case, one method is way better than the other. The other method doesn't work. This will probably do elimination instead. It's not going to do substitution. Do what? Not going to do SN1 most likely because cyanide is pretty strong. So it's going to be bimolecular. Bimolecular SN2 is out, so it'll probably do E2. So there are 2 new ways to make carboxylic acids to go with your 4 old ways. Okay, now we're going to move to reactions. Any questions about those above? By the way, I don't think we labeled it. When the Grignard enters the CO2, what type of reaction is that? How do you want to describe that reaction? Nucleophilic addition. Okay? And by the way, when we did nucleophilic addition to aromatics, we said that the resulting anion has to be where for the reaction to really work. On an electronegative heteroatom. When we did nucleophilic addition to CO2, where did the minus end up? On an electronegative heteroatom. The oxygen, right? particularly when we do nucleophilic addition to a pi bond. It only works if the resulting anion can end up on an electronegative heteroatom. We're going to see that many more times. Okay, reactions occur by acrylic acid. Now that we know how to make them, we have a toolbox of methods to make them. First reaction is to an acid chloride or acyl chloride. Okay? Can we work with thionyl-chloride? This is analogous to, remember back during week 1, we did this. Okay, it's analogous to that. OH to Cl, OH to Cl. But the mechanism is a little bit different, because here that's an sp3 carbon, but here it's an sp2. And over here we did like an SN2 substitution maybe. We don't do that here. Okay. Thionyl chloride. Sulfur is electron deficient. It's got all these greedy atoms pulling on it. Now I have to decide, do I want to lie to you and make it easy, or do I want to tell you the truth and have a little more discussion? Well, at some point we're going to have to do it right, and then you're going to have to say, well, why did we do it back then? Okay? I'm going to try to tell you the truth. It won't be too painful. Okay, what's the first step? This attacks here. Which oxygen is going to attack there? This one. This one. Why that one? More acidic? There's not even H on that oxygen. I mean, it's not acidic. If you do resonance structure here, you'll see that that oxygen has some partial positive charge. Why would a partial positive oxygen attack a partial positive sulfur? It would not. One of these lone pairs is in a p orbital. That's going to make this oxygen not that basic. Neither one of these are in p orbitals. In the end, we're going to react right here. These electrons here. Now when we attack this sulfur, what do you want to do? Kick off a chlorine? No. We're going to break the pi bond. This is just like tosyl chloride. Okay? And if you haven't noticed, I try to build on consistencies. Okay? What did we do before? We're doing it again. We're going to do it again. Okay? So what does this give? I'm just going to call this R. So we got R, OH. Now this oxygen is now bonded to the sulfur. Sulfur has 2 chlorines, and it has a single bond to O, but that's now minus. Because what does this arrow mean? We're down. This arrow means these electrons are moving up on the oxygen and becoming the third lone pair. And we just made this. Now, everything over here is neutral. 2 neutrals. How do 2 neutrals react to give a minus? They don't. 2 neutrals, this has to be neutral. Where is the positive charge to make this net neutral? Right there. You cannot just take 2 neutral molecules and react them and create a positive charge. Look back at your mechanisms on the test. Okay. At this point, we can draw resonance here. Let's take this, move it in. We're going to come back up there and do chemistry up there. And let's move this out here. Does everybody agree that this is resonance? And this gives you that there. Everybody agree that's a resonance structure? Electrons in, electrons out. All we did was move pi electrons. We didn't move any atoms. Real quick, you may not even want to write this down. What if we had reacted here on the sulfur? That would have given if the OH had reacted with the sulfur, we would have gotten that. Does everybody agree? Does this have resonance? How you going to draw resonance? Move these down and leave that with no octet? Don't do that. That oxygen will hunt you down. No resonance. So, would you rather form a positive over here that has resonance or no resonance? Resonance. Delocalize the charge. That's why it attacks on this oxygen. No reason. Okay? If I had lied to you and just went on and did that, then we'd see this nice resonance. A resonance delocalized approach is always better than a non. Okay. At this point, let's come back up here and work with this. What did we do? This was a nucleophilic addition. Where do we put the minus at? On a heteroatom. Okay, at this point, what can this do? Anytime you can reform a pi bond and kick off a leaving group, that's easy to do. What does that give? We now have that with 1 Cl plus Cl minus. Still net neutral, minus and a plus. Everybody with me? We do have to make these two. What do you want to do next? I see an opportunity to make HCl. These electrons take the H, move behind. What does that give? That's now neutral oxygen, O, S, O, Cl, plus HCl, right? Actually, I should not have done that. Do it. There's nothing wrong with what I did. I mean, arrowed correctly. That movement gives that. The problem is, I now don't have a Cl. So let's call all this A, and that's A. Let's do something differently. Instead of that, instead, let's have these electrons attack here and give this oxygen electrons by moving these here. What does that give? By the way, what are we trying to ultimately do? We're trying to get a chlorine on that carbon. Right here, we can do that. We can bond it here. So now we have OH. Oxygen becomes neutral, so it's happy. Chlorine there. And we have O, S, Cl. Would that give that? Okay. Now, you may say, well, this is kind of a long mechanism. What we're doing here is very fundamental steps that we're going to be doing with every mechanism. Okay. Now, at this point, what do we want to accomplish here? From here. We'd like to make a carbon-O double bond. If we can make this be a double bond, Are we trying to eliminate anything? We want to get rid of this oxygen. Anytime you can make a pi bond and kick off a leaving group, that's easy to do. Just going to keep track of how many times we say that. I'll erase this one so we can come this way. What does that give? You got to know what you're. This means pi bond here, so we got here. There's an H still there. You can't just lose the H. One not there. That happens to be a plus charge. Chlorine plus the leaving group. What was the leaving group? O. That's somewhat analogous to a tosylate. It's only SO instead of SO2, and that's a chlorine instead of a toluene. What do we need to do to get final product? Jason?
Why wouldn't it kick off the CL and stuff?
It theoretically could. Let's see. If it did, what would we get? We get back this. Yeah. Every step here is probably reversible. It could. But that's not going to get you to, you got to have a seal on the carbon. So you're going backwards if you do that. Every step is reversible. Maybe half the time it kicks off the chlorine, half the time it kicks off this. You could even argue that this is a better leaving group because all this withdrawing. At least that's an argument. What do we need to do to get this to be final product? Something needs to take the H. What's going to take the H? Do what? I could have this take the H and we might think we'd be done. But we got to make SO2. Plus ultimately HCl. At this point, this actually decomposes because anytime you can make a pi bond and kick off a leaving group, that's easy to do. I'm going to come way over here. What does that give? It gives SO2 plus what? Cl minus. Now what can take the H? This takes the H. What do you get? You get the neutral and you make HCl. There's lots of fundamental things built into this mechanism. Every step you should look at why did we do that. Starting with why did we attack with this oxygen? Why would we add here? Why did we kick the chlorine off immediately? Because you just don't do that. You break the weaker bond. We talked about that week 1. Anytime you make a pi bond, kick off a leaving group. Okay? It's very worthwhile. This sets us up to do lots of the chemistry moving forward. Ultimately, we did addition. What do you want to call this step here? When we came in and eliminated the chlorine. Elimination. We also then did, what do we do over here? Elimination. Right here. When the chlorine added here, what was it? What do you want to call this? Addition. When the chlorine was eliminated, what do you want to call that? Elimination. Many of the mechanisms we will do will involve addition and then elimination. Okay. Let's see. So, next we'll do conversion to esters. So, what did we just do? We just showed how to convert an acid to an acid chloride. Now you can put a reagent on that line. Next we will show how to convert this to esters. Okay? So that's your kind of your organization there. The green is your outline. Probably now, I sometimes do this first, and we didn't do this first. We will now look over here, and we will show addition elimination. And when we look at this, we'll refer to what we just did. We kind of did it first, but now we'll look back and review. We'll do that next time. See you here at 1 o'clock if you want to attend the career event. There'll be like 4 panelists who work in industry and some type of science field talking about what they do, giving you some pointers. 1 o'clock right here.